So in this video, I'm going to explain about the deletion operation of AVL tree. So AVL tree is nothing but AVL tree is also one type of the binary search tree. Binary search tree, whenever I say that binary, it means that a node is having 0, 1 and 2 children. Right. Next is saying that binary search tree. Binary search tree, it means that the left children always be less than equal to and right children should be the greater than. So right children should be greater than and left children should be less than equal to root node. So this is the true property. If it is you are going for the AVL binary search tree. So AVL tree is nothing but also called binary search tree because AVL tree is a binary tree. Every node is having 0, 1, 2 children. And another is that left children should be less than equal to root node and right children should be greater than. Third property is that balance factor. Balance factor means each and every node balance factor should be in the range of 0, 1 and -1. If it is, the range will not in this if it is the balance factor of node is not in this range, then we can say that it's not following the AVL tree property. Then we will going to perform some rotation, and there are 4 rotation in the AVL tree that I have already explained in the previous video. So here I am going to perform the deletion operation in the AVL binary tree. So before going to the AVL binary tree deletion, first we have to know that binary search tree deletion, because AVL tree is a binary search tree. Means first you have to know that binary search tree deletion, then you can easily understand the AVL deletion, because AVL binary search tree deletion is also similar to the binary search tree deletion, but difference is that you are using the balance factor concept, because you are trying to make a binary search tree to be balanced. So only one thing is that you are just trying to make a binary tree should be balanced. For that reason you are using the balance factor, and that's why it's called AVL tree. So now this is the we'll see that the 3 case for the binary search tree deletion. So there will be the 3 case of binary search tree deletion, because binary tree is having a node binary tree is a node is having 0 children, 1 children and 2 children, then only we can say the binary tree. So there are 3 cases in the binary search tree deletion. If you perform deletion, you will get 3 cases. One case is that if you are going to perform, suppose here I am deleting the node is 31. Suppose I am going to delete the 31. So first I will find out where is the 31. So binary search tree is saying that left children always be less than equal to. So first check that 31 is 31 less than equal to 11 or greater than 11. So it's a greater than, so come to the right part. Now check that is 31 is less than 19 or greater than. So 31 is greater than, come to the right part. Here check that is 31 is less than 43 or greater than. So it's a less than, so 31 will come to the left part. So now you got here 31. Now you reach to the 31, but here what operation you are performing? You are performing deletion operation. So what will you do? You have to perform delete. But how you delete? Because you are working here, you are performing the binary search tree deletion. So how you have to delete that? So for here the binary search tree case 1 is saying that if a leaf node, means a node is having 0 children, leaf node means a node is having 0 children, we simply delete. So we simply delete this 31. We simply delete 31 and we will not going to do anything. So this is also the binary search tree. Still it's following the binary search tree property. If it is the leaf node, if you are going to delete the leaf node, so even after deleting you will going to tree will again following the property of the binary search tree. It's not violating the property. Now coming to the delete the 4 node. Suppose I am going to delete the node, that value will be 4. So first I will check that where is the 4. So I will start from the root node. 4 is less than 11 or greater than. So less than, I will come to the left part. I will check here 4 is less than 6 or greater than. So 4 is less than 6. So I will come to the left and I will see that 4 is in the left part. So I reach to the 4. Now I am going to perform deletion. So deletion, if I am going to perform 14, so first I will check that what type of case it is. So case is saying that a node is having 1 children, either left and right. It's not a matter. Here we were not talking about the left children and right children. We were just talking about a node is having the single children. So 4 is having the single children. So for that situation, how you have to perform deletion? Because if you simply delete 4, if you simply delete 4, what happened, that complete tree will become the one separate tree, and that 4 is become the separate, 5 is become the separate tree. But that's not good. That's not a binary search tree property. That's not saying. So for that situation, even after the deletion of the 4, still your tree will be the binary search tree. So for that case, what it is saying, that if it is a node is having, if it is a node is having single children, then how you perform deletion operation? How you perform deletion operation? So for that situation, it's saying that you make that the children of the 4, make that the children of their parent. So now the 5 became the children of 6. The 5 will become the children of 6, and then after you delete 4. The case 2 is saying that if a node is having one children, link the parent with this children. First we have to link this 5 to 6, and then we have to delete the 4. So this is the second case of the binary search tree deletion. Now there is a third case. Because why we have a 3 case? Because a node is at most 2 children possible in a binary tree. That's why this is the third case. Third case is saying that if a node is having 2 children. We have already seen that a node is having 0 children, node is having 1 children. Now the third case is that a node is having 2 children. For that situation, what will you do? If it is 2 children, how will you perform deletion? So after the deletion, still your tree will be the binary search tree. So how you perform deletion? So for that situation, what will you do? You have a 2 option here. If it is a node is having 2 children, so for that situation you have a 2 option to swap it, and then after you will get that, even after the deletion you will get the valid binary search tree. So here suppose if I am going to delete 11, suppose if I am deleting 11, so for 11 is having 2 children, 6 and 19. So how you have to delete this 11? If you delete if you delete 11, it will become the both separate tree, and that's not a binary search tree, right? So for that situation, what will you do? So you have a 2 option. Here I have written that either swap 11 with 10. It means that here what it is saying, that either you have to swap maximum of left subtree, either you swap 11 with maximum of left subtree, or see here I'm using the word is either. Either it means that either you use this one, or either you have to come to the right part. So if you are taking left side, then you will swap this 11 with the maximum value from the left subtree. And if you are not taking left side, then you will take right side, and that from right side you will take minimum value. If you are taking maximum from left side, that's called in order predecessor. That's called in order predecessor. And if you are taking minimum from right side, that's called in order successor. That's called in order successor. So you have to follow either one. If you are following in order predecessor, you follow in order predecessor. If you are following in order successor, then you follow in order successor. But only one at a time, you only follow one. So if you are following deletion operation and you are taking that in order predecessor, then you have to always take in order predecessor for whole deletion. Whole element deletion means whole binary search tree. If you are performing deletion operation, if you are deleting 11, 6, like that if you are deleting, so for that situation you always follow the in order predecessor only. Don't follow in between in order successor. Sometimes in order predecessor, sometimes in order successor. No, that you don't follow. If you are following in order predecessor, then only follow in order predecessor. So this is all about the binary search tree deletion. Now I will going to explain the AVL tree deletion. If you understood this one, you can easily understood that AVL tree deletion operation. So now this is the given AVL tree, and we can also say that binary search tree. This is the AVL tree. Now I am going to delete. These are the element one by one. I will going to delete. So first I am going to delete here 88. First I am going to delete 88. and this is the given binary search tree. So 88, I will check that where is the 88. So I'll start from the root. Is 88 greater than 33 or less than? So 88 is greater than, come to the right part. Is 88 is less than 77 or greater than? So greater than, come here. You reached here. So you got the 88. Where is the 88, right? Now check that is 88 is having 0 children, 1 children or 2 children. So here 88 is having 1 children. Here 88 is 1 children. So just now I have explained that if it is a node is having 1 children, then you have to link 88 parent with the 88 children. So 77 is the parent of 88. Now 99 is become the children of 77. It's became, now you delete that 88. Now you delete the 88, right? So after the deletion you got this tree. After the deletion you will get this tree. Then this is the just a binary search tree deletion. You perform just binary search tree deletion because we were binary search tree deletion. But here I am explaining about the AVL tree deletion, right? So a binary search tree deletion done. Now AVL tree deletion. First, what will you do? You have to first delete the element. I have deleted. Next step, you have to calculate balance factor of each and every node, because you have to also check that your tree is balanced or not, right? So you have to also check that your tree is balanced or not. If it is not balanced, then you perform rotation, and that rotation also there are 4 rotations that I have already explained. That is LL, RR and LR and RL. So for LL you are performing 1 rotation, for RR you are performing 1, for LR you are performing 2, and for RL you are performing 2 rotation, right? So now coming to here, I have calculated balance factor of each and every node, and I have seen that all these coming in the range of 0, -1 and 1. So it means that my tree is balanced here, so I am not going to perform any rotation here. So I have deleted 88 and my tree is still following the property of the AVL tree. So I am not going to perform any rotation. Now my next element 88 is deleted. Now my next element is 99. So I'm going to delete the 99. So for 99 again I start from the root node. I'll first find out where is the 99. So I'll came 99 is greater than 33, 99 is greater than 77, and I got 99. I reached 99. Then after first I reached the 99. Second step, what will I do? I will check that is 99 is having 0 children, 1 children and 2 children. So here is that case 1, means 99 is following 99 is having 0 children, means leaf node. So we simply delete. So I have just deleted 99. I have deleted 99. And after the deletion I got this tree, and after deletion I have calculated balance factor. After the deletion I calculated balance factor. So when I calculate balance factor, I hope you already know that how to calculate balance factor. Balance factor is nothing but a height of left subtree minus height of right subtree, and that range should be 0, 1 and -1. So this is the balance factor calculation. So if you calculate balance factor of 11, means there is no left, there is no right, means 0 minus 0, you will get 0. So here 15 balance factor is left tree is 11, but there is no right children, means left minus right I am saying that. So left means 1 minus 0, it means that 1 only. So like that you can calculate balance factor. So here I have already calculated. So after the deletion of the 19, I got that binary tree and I calculated balance factor, and I have seen that there is a violation occur. So there is a violation at 77. There is a violation at 77. Right? Now what will you do? Because violation occur here. So now what will you do here? So for that situation, look at that, the situation is what? If you see here, you will how you have to perform how you perform the rotation. So you will get the balanced one. So you will see that there is a 2 case here. There is 2 case. Either you have to perform, this situation is what? LL situation. This is LL situation. Another is what? Another is this 3. We are always performing rotation between 3 notations. So this is what? LR. Right? So don't confuse here. This is very much important, guys. Try to understand. This is very much important. Here you will get it the two situation. One situation is you are getting that LL, and another situation you are getting the LR. So if you perform, either you perform LL or either you perform LR situation, right? So either you perform LL rotation or either you perform LR rotation, both will going to give you that balanced one. But here is saying that which one will you select? Because you have a two option. In two option, which one will you select? You always, of course, everyone will select the lesser rotation, because LL is performing single rotation but LR is performing two rotation. One is that left rotation, another is performing right rotation. See, here you are performing two rotation, here you are performing single rotation. So always go for the single rotation. So here if you get this type of situation, if you are performing deletion in the AVL tree and if you are getting this type of situation, always go for the single rotation. Don't go for the double rotation, because every rotation will take some time. So why you want to waste the time if you have an option for the single rotation? So if you have option for the single rotation, don't go for the double rotation. So if you are getting situation, sometime might be you will get that RR and another you will get that RL. So that time also go for the RR, don't go for the RL, because this will take two rotation and this will take one rotation, right? So you always go for the less number of rotation. So here you do perform rotation between 17, 15 and 35. Do perform rotation between this three node, not to this three node, because this will take two rotation. That's not preferable. You go for this rotation, that will take only single rotation, and after the performing rotation, here LL means we have to perform right rotation, and that too from what? From mid node. That too from mid node. So 55 become root and 77 goes down and 35 come in the left part, right? So after the rotation you will get this one, right? So you have performed rotation. Now you have to add the remaining tree, right? Now you have to add the remaining tree, right? So if you add the remaining tree, where the 66 I'll erase for the better understanding, so you will get that correct concept. Okay, so I'm just erasing this part. So now I'm going to insert that all the remaining tree, right? So remaining tree is that 66, where the 66 is going to insert. So 66 is right children of 55. So first I have checked that right children of 55, that is already 77. Now we'll see that where 66 is going to store. So right 66 is the right children of 55, but that's already 77. But where 66 is going to store, so 66 will not going to make that right children, because right, it's a binary search tree and right children always be greater. So right 66 will come to the left part, right? 66 is come to the left part. Now the 33 is going to store where 33 left children was right children was 77. So if you check that, the right children is 77 and 55 is also 55, the parent of the 77. So 33 is going to connected with the 55. The remaining part you simply add it, right? So after this addition, after the addition, you will get the new tree, and that tree will be this one. That tree will be the this one. After the performing the rotation, you will get this tree. After the rotation, you will get this tree, right? So far you have deleted 88, 99, and after the 99 deletion, your tree was violated the property. Then you have performed rotation. Now I am going to delete a 22. Now I am going to perform 22 deletion operation. So now I am going to delete 22. So if I am going to delete 22, first I have to check that where is the 22, and that to start from the root node. So root node 22 is the lesser value, so you come to the left part, here you got the 22. Now I am going to perform delete 22 deletion. Before deleting, you have to check that which situation it is. Is 22 is having 0 children, 1 children and 2 children. So here is that 22 is having 2 children. So what will you do? So just now I have said that previous video what I have taken that, I have taken that in order predecessor, means we have to take maximum from the left tree. We have to take maximum from the left subtree. So what is the maximum? maximum is that 15. Maximum is the 15. So first I have to swap 22 with 15. First I am going to perform swapping here from 22 to 15. So here what happened that 20 will come here and 22 will come here and 15 will goes up, right? So this, forget over this one. Now this is changed, the value is changed. So 15 goes there, 22 come here, because I have to perform deletion. So far I haven't deleted 22, I haven't deleted, I just swapped. Now again check that which situation it is. Is 22 is having 0 children or 1 children or 2 children? So 22 is having 1 children. If it is 1 children, then what will you do? You make that the children is parent of 22. The now 11 become the children of 15. Now 11 become the children of 15. So now this connection is deleted. Now this connection is deleted. Now you easily delete 22. I hope you understood. If you have doubt, then again I'll explain it again. Again I explain this. I'll erase it first and then I'll explain. So now I'm going to delete 22. So for deleting the 22, I came 22. Now 22 is having 2 node. So 2 nodes. So there is a 2 situation. I have already explained the previous slide. If it is 2 children, you will take that either you take maximum from left or minimum from right. So here I am taking maximum from left. Here I am taking maximum from the left. So maximum is what? 15. Maximum is the 15. So I will going to swap 15. I am going to swap 15 with 22. So 22 will come down, 20 will come down and 50 will goes up. So far I haven't deleted, right? So 22 came here. Next again you have to check that what situation it is. Is 22 is having 0 children, 1 children and 2 children. So 22 is having 1 children. So in that situation how you perform deletion? So in this situation you perform that, you make that the children of 22 make that children of 15. So now this connection is deleted. Now this connection is deleted and 11 is become the children of 15. 11 is become the children of 15 and then after you perform deletion 20. So I have performed this one and after this performing I got this tree. So this is deleted, 22 is deleted now, 22 is deleted now. Now I will calculate the balance factor of each and every node. So I have calculated balance factor of each and every node and I have seen that all these in the range of 0, -1 and 1. So this is already in the AVL tree. So not required any rotation. Now I am going to delete the 33. Now I am going to delete 33. So for deleting the 33, what will I do? I will going to take left. I always prefer here because I am always here using what? Taking maximum from the left. Here I am taking maximum from the left and then after performing swapping and then again I am checking the case. So same thing I will going to do here. So now the 33 is going to swap with what? Here I am performing deletion 33. So now 33 is going to swap with what? 25. So 33 is swapped with 25. So 25 will come here and 33 will come here. Right? Next what will you do? 25 came there. For 33 you haven't deleted it. Now check that is 33 is in which situation. So now 33, if you see that this is the leaf node, so you have simply deleted the 33. So I have simply deleted the 33. After the deletion of the 33, I got that after this deletion of the 33, I got this tree. Right? Now I calculate the balance factor of each and every node. I will calculate the balance factor of the each and every node, and if you see that all these balance factor in the range, so not required perform any rotation. So I haven't performed anything here. Now my next node is that 11. Now I'm going to delete the 11. So for that reason again I have to check from the root node. Where is the 11? So 11 is the lesser value 25, then 11 is the less than 15, then I'll come here and I have seen that 11 is the leaf node, so I have simply deleted, and after the deletion of the 11 I'll calculate the balance factor of each and every node. So I have after the deletion of the 11 I calculated balance factor of each and every node and I got this tree, and I have seen that there is a violation occur here. I have seen that violation at 25. So for the violation here what will you do? So again you will take the 3 node. So left side is, there is a single node, so you will not going to perform rotation in the left side. You will not going to perform rotation in the left side, you perform rotation in the right side. So from that situation, what will you get here? Again you will get it the two situation. Again you are getting the two situation. One situation is that you are getting that RL. Another situation you are going to get that RR. So again you select only one. You select one, and that too is single rotation, that you have to perform that RR rotation. You have to perform RR rotation, right? So I will explain you that how you perform this RR rotation and how will you get that the tree. So here you have to perform that RR rotation here in between the 25 and 15. So you, after this rotation performing, you will get that you are performing left rotation from the mid node. You are performing left rotation from the mid node. So you will get it here 55, and left will be the 25 and right will be the 77, right? So that is done. Next, what will you do? Next you have to add the remaining node. 66 is the left children of 77, so 66 is added here, and 35 is the left children of 55, so 25 is already in the left, so 35 will become the right children of the 25, and 15 is the left children of 25, so 15 is added here. Now again you calculate the balance factor of each and every node. So 15 balance factor 0, 35 is 0, 66 is 0, and 77 balance factor will be the left children is 1, so 1 minus 0, that will be 1. For 25 left is 1, right is 1, it means that their balance factor will be 0. For 55 balance factor is 0. So this all this node balance factor coming in the range, so we will not going to perform any rotation. This is still bind AVL tree. Now I am going to perform deletion. Now 88 is already deleted, 99 also deleted, 33 also deleted, 11 also deleted. Now I am going to perform 15 deletion. Now I am going to delete 15. So if I am going to delete the 15, first I will check that where is the 15. So is 15 is less than 25? Yes, less than, so it came here. So now if you delete 15, if you delete 15, check that which situation it is. 15 is having 0 children or 1 children or 2 children, so 0 children, so we have simply deleted. So if I am going to simply delete 15, if I am deleting simply I will delete the 15 here. I have deleted. After the deleting, I got this tree. After the deletion of the 15, I calculated the balance factor. So first I have deleted 15 here. So this is assumed that this is deleted. This 15 is deleted. Now I have calculated balance factor. So 15 is deleted from here. Now calculate the balance factor of the each and every node. So 25. So right will become the 0. 0 minus 1, it will become minus 1. For 55 there is a single height. This is single height will be the 2 here. So 2 minus 2. So this will be the 0. Sorry, this height will be the 0 here. This height is 0 here, and 70 height is 1. Balance factor is 1 only, right? So still it is in range, so there is a not required any rotation. So 15 is deleted. Now next element is 35. Now I'm going to delete the 35. So for deleting the 35, see, look at that, I have done mistake here. This is 0. This is 0. So now I'm going to delete the 35. So first you have checked that where is the 35. So again you follow the same process. Start from the root and come to the 35. So I came to the 35. I have seen that 35 is a leaf node. So I am simply going to delete the 35. So 35 is deleted now. After the deletion of the 35, again I will going to calculate the balance factor of each and every node. So I have calculated the balance factor. 25, there is no left, no right, so it will be 0. For 50, there is a right is 1 children, and left is having 2, means 1 minus 2, you will get that minus 1. For 77, 1, and 66, 0. Right? So again this is in the range, so there is a no rotation required. Now I am going to delete that 66. Now I am going to delete the 66. So for 66, again check from the root node. Where is the 66? So 66 is less than 55 or greater than, come to the right part. Now check that 66 in the left part, so this is also leaf node, you simply delete. After the deletion, you calculate the balance factor. After the calculating the balance factor, you will get that each and every node is having balance factor is 0, means all these are balanced one. so no rotation required. Now you delete the 77, then again come to the 77. 77 is the leaf node, so simply you have to delete 77. Now afterward if you calculate the balance factor, you will get the tree is like 55, 25. 55 balance factor is now 1 and 25 is 0. Now you delete the 55. So if you delete the 55, what will you do? You have to make that you delete the 55, 25 is become the single node, right? So 25, there is a no parent here, there is no parent, so you will not going to connect with that. So 25 is the become the single node and 55 is deleted, and this is balanced one. So that's all about the AVL tree deletion operation. And the time complexity of the AVL tree operation is order of log n. Order of log n. Guys, don't confuse that what is the time complexity. The time complexity of the order of log n, because this is the already binary search tree property, and you are binary search tree and you are performing deletion operation, and you know that the height of the binary search tree or balanced one, the height is order of log n. So that's the reason the time complexity is order of log n. So that's all about the deletion operation in the AVL tree. Thank you for watching my video. Next video I am going to explain about that red black tree. If possible, I'll make one separate video for the important question for the GATE as well as the competitive exam like NET exam, NILET exam and BARC. That's very much important. I will make separate video for them for that question. And for this video, all about the deletion operation.